Turn on a tap tonight, just a little, and look at the water. For the first few centimetres, it does not behave like a liquid at all. It is a clear glass rod, still enough that you can see the sink distorted through it. And then, somewhere down its length, it goes white and breaks apart into a churning rope. There is a boundary between the two, and you can point at it. Nobody on Earth can calculate where that boundary will be. We have had the equation governing that water since 1845. It has never once been caught being wrong, and it is used to design every aircraft you have ever flown in. Every problem in physics has an answer, or at least a clearly shaped hole where the answer will go, except one. By the end of tonight, you will know exactly which problem that is, and why it is the one that matters most. Before we start, if you enjoy sitting with a question nobody can answer, a like or subscribe would mean a great deal to me. It really does help me keep making these. Now, let's ease in. There is a place, a few centimetres below the spout of every tap in the world, where physics stops being able to tell you what happens next. You have looked at it 10,000 times without noticing. Go and turn a tap on, very slightly, and watch the water leave the spout. For the first stretch of its fall, it is not really behaving like a liquid at all. It is a rod, a clear, still, glassy column, smooth enough that you can see the shape of the sink distorted through it, steady enough that it looks like something you could take hold of. The surface has no features, nothing moves across it. If you put your finger near it without touching, the column does not react. It simply falls, unchanged, holding its shape. And then, somewhere down its length, it stops doing that. The clear rod goes cloudy. The surface roughens, breaks into ripples, and then into a churning white rope that hisses faintly into the basin. The transition is not gradual. There is a region where the water is glass, and a region where the water is chaos, and between them there is a boundary you can point at. Now open the tap a little further and watch that boundary move. It climbs. The glass section shortens, the chaotic section lengthens, and the point where one becomes the other travels up toward the spout. Open the tap far enough, and the smooth part disappears entirely. The water is disordered from the moment it leaves the metal. Here is the thing I want to sit with tonight, before anything else. Nobody can tell you where that boundary will be. Not approximately. There are engineers who can give you a decent estimate, and there are correlations fitted to laboratory data that will get you into the right neighborhood. But nobody can calculate it. Nobody can take the shape of your tap, the pressure in your building's pipes, the temperature of the water, feed those numbers into the governing equations of fluid motion, and derive the exact height at which the column will break. It cannot be done. Not with more care, not with more time, not with a bigger computer. The calculation is not merely difficult. It is, in a sense, I am going to spend the next 2 hours making precise, out of reach. I want to be clear about how strange that is, because the strangeness is the whole subject. Physics has answers for the ridiculous things. We can tell you what happens to time inside a gravitational field so intense that light cannot leave it. We can predict the magnetic behavior of a single electron and get agreement with experiment to 12 decimal places, which is roughly the accuracy of measuring the distance from London to New York and being wrong by the width of a human hair. We can describe the first fractions of a second after the beginning of the universe. We can tell you the date and the minute of a solar eclipse 3,000 years from now, and we can tell you where on the surface of the Earth its shadow will fall, and the calculation will be right. 3,000 years, and we cannot tell you what the sky will do in 3 weeks. We cannot tell you where the water breaks. We cannot tell you which way the smoke will curl off a blown-out candle. We cannot tell you, from first principles, exactly how much fuel an aircraft will burn crossing an ocean. The airlines know, but they know because they have flown the route thousands of times and measured it, not because anyone derived it. We cannot compute the drag on a ship's hull. We cannot predict the pattern of cream folding into coffee. These are not exotic failures at the edges of knowledge. They are failures in the middle of the kitchen. The phenomenon behind all of them has a name, and it is a name that has been quietly demoted in ordinary speech until it sounds like nothing much. Turbulence. Most people know the word from an announcement on an aeroplane, a small inconvenience associated with a seatbelt sign. What the word actually means is the chaotic, irregular, self-generating motion that almost every moving fluid on Earth falls into as soon as it moves with any real vigor. It is the state of the air in this room. It is the state of the water in every river. It is the state of blood in the larger arteries, of air in the upper airways of your lungs, of the gas in the outer layers of the sun, of the gas between the stars, of the atmosphere over your house tonight. Smooth, orderly flow, the glass rod at the top of the tap, is the exception. It is a fragile special case that survives only in thin films, in narrow tubes, at low speeds, in the slow ooze of a glacier or the crawl of honey off a spoon. Everything else, everywhere, is turbulent. The universe moves its fluids chaotically, and it does so as the default. It is worth pausing on how hard that smooth section is to keep. Smooth flow is not the natural resting state of a fluid that something merely disturbs. It is a condition that has to be actively protected, and it collapses at the slightest excuse. Aircraft designers have been chasing laminar flow over wings since the 1940s, because a wing whose boundary layer stays orderly experiences a fraction of the friction of one whose boundary layer does not. The engineering is achievable. The problem is that the surface has to be kept close to surgically clean and smooth. A line of dead insects picked up along the leading edge during takeoff is enough. A few millimeters of accumulated grime, a slightly proud rivet, a scratch. Any of these will trip the flow, and once it has tripped, it stays tripped for the rest of the wing. Order in a fluid is a house of cards. Chaos is the floor it falls onto. And this ordinary, everywhere, unavoidable thing is, by a broad and rather uncomfortable consensus among the people best placed to judge, the last great unsolved problem of classical physics. It is not even confined to the kind of matter you would expect. Turbulence appears in the convection zone of the sun, where columns of plasma, the size of continents, rise and shred. It appears in the disks of gas spiraling into black holes, where it is the mechanism that lets matter shed angular momentum and fall inward at all. It appears in the clouds of gas between the stars. And it appears, this is the part that should not be possible, in superfluid helium cooled to within a couple of degrees of absolute zero, a liquid with literally zero viscosity, where the chaos organizes itself into a tangle of vortex lines each carrying a fixed quantum of circulation. A fluid with no friction still finds a way to become turbulent. It just does it in discrete units. I want to test that phrase because I think it sounds like an exaggeration, and it is not one. Classical physics means the physics of the ordinary world. Forces, motion, heat, pressure, fluids. It is the part of the subject that everyone agrees was finished a long time ago. The unfinished business of physics is supposed to live somewhere else entirely, down at the scale where quantum mechanics and gravity refuse to reconcile, out at the boundary of a black hole, back in the first instance of the universe, off in the dark matter that we can weigh but cannot catch. Those are the famous open questions, and every one of them is somewhere you cannot go. Turbulence is in the sink, and the equations that govern it are not missing. That is the part that turns this from a curiosity into something genuinely disorienting, and it is where we are going next. This is not a case of physics not yet having found the law. The law was found. It was written down almost 200 years ago. It has been tested continuously ever since. It has never once been caught being wrong. and it is used every single day by every wind tunnel, every weather center, every engine designer, and every heart surgeon's simulation software on the planet. We have the equation. We have had it since before the invention of the telephone, and we still cannot answer the question. So the question I want to put to you, and hold open, and not answer until the very end of tonight, is this one. Every problem in physics has an answer, or at least a clearly shaped hole where the answer will go. Except one. And I want to know why that one is this one. Why the problem physics cannot solve is not the black hole or the beginning of time, but the water coming out of your tap. To get there, we are going to need to meet the equation itself. In 1822, a French engineer named Claude Louis Navier wrote down an equation for how a fluid moves. He was not, at the time, trying to solve one of the great problems of physics. He was a bridge builder. He worked for the Corps des Ponts et Chaussées, the French state body responsible for roads and bridges, and he spent his professional life on suspension bridges and the mechanics of the materials they were made from. The fluid work was a sideline, and there is a detail about it that I find quietly wonderful, which is that his physical reasoning was wrong. He arrived at the equation by imagining forces acting between the individual molecules of the liquid, a picture that does not survive contact with modern physics. He built the right answer on the wrong foundation and did not know it. 23 years later, in 1845, an Irish mathematician working at Cambridge named George Gabriel Stokes derived the same equation properly. Stokes came at it from the behavior of the fluid as a continuous substance rather than as a crowd of molecules, and his derivation is essentially the one still taught today. Between the two of them, 3 others got there independently and are mostly forgotten for it. Cauchy in 1828, Poisson in 1829, Saint-Venant in 1843. 5 people found the same thing within 21 years of each other, which usually means an idea has become ripe. Stokes himself is one of those figures whose name is scattered across the sciences like loose change. There is Stokes' theorem, which is one of the central results in vector calculus. There is the Stokes shift, which describes how a fluorescent material re-emits light at a longer wavelength than it absorbed. There is the Stokes, the unit in which kinematic viscosity is measured. He worked on the wave theory of light, on the behavior of pendulums in air, on why the sky is the color it is. He was Lucasian Professor of Mathematics at Cambridge for over half a century, the chair Newton had held and Hawking would later hold. The fluid equations are, by a considerable margin, the least famous thing he did during his lifetime, and the most important thing he did in the long run. What they found is now called the Navier-Stokes equations, and I want to tell you what they say without any mathematics at all, because the content is much simpler than the reputation. Take any small parcel of fluid, a cubic millimeter of the water in front of you, a thimbleful of the air in the room. Newton said 150 years earlier that a thing accelerates in proportion to the force applied to it, and in inverse proportion to its mass. The Navier-Stokes equations are that statement, and nothing more, applied to a fluid parcel. They say, the acceleration of this parcel equals the sum of the forces on it. There are 3 kinds of force. There is pressure, pushing on it from the surrounding fluid. There is viscosity, the internal friction that resists one layer of fluid sliding past another, dragging fast parcels back and pulling slow ones forward. And there are external forces, like gravity. Add them up, and you know how the parcel accelerates. Do that for every parcel at once, and you know how the fluid moves. That is it. That is the whole content. Newton's second law, written for something that flows. These equations have been in continuous use for 180 years, and in that time, nobody has ever produced a physical situation within their stated domain in which they give the wrong answer. Every wind tunnel result is compared against them. Every weather model on Earth is a numerical approximation of them. Every aerodynamic surface, every pump, every pipeline, every artificial heart valve, every combustion chamber, every ventilation system, in every building you have ever been inside, was designed with them. They are not controversial, not provisional, not awaiting replacement by a deeper theory. There is no serious physicist anywhere waiting for the Navier-Stokes equations to be overturned. We have the law. That is the point I need you to hold on to for the rest of tonight, because everything else depends on it. This is not a story about a missing piece of physics. And now, the strange part. Having the equation does not give you the answer. You can write down the law that governs every parcel of fluid in the universe, be certain that it is correct, and still be entirely unable to say what the fluid will do. Those turn out to be two completely different achievements, and the gap between them is not a technicality. It has swallowed 180 years of effort by some of the most capable mathematicians who have ever lived. I want to say that sentence again in its plainest form, because it is the sentence this whole video is built around. We can write the law and still not know the outcome. Sit inside that for a moment, because it is genuinely unusual, and I do not want it to slide past as a clever paradox. In almost every other case where physics cannot predict something, we can name the missing ingredient. We cannot predict what happens at the center of a black hole because we do not have a theory that combines gravity with quantum mechanics. The ingredient is a theory, and we know we do not have it. We cannot say what dark matter is because we have not detected the particle. The ingredient is an observation, and we know we are missing it. In each case, there is a clearly shaped hole, and everybody can see its outline. Here, the hole has no shape. There is nothing anybody can point to and say, if we had that, we could do it. The equation is complete. The initial conditions can be measured. The physics is ordinary, classical, non-relativistic, and non-quantum, in the part of the subject that was declared finished before anyone alive was born. And the answer is still not obtainable. The obstacle is not ignorance about the world. The obstacle is that the consequences of a known law can be, in a way that turns out to be mathematically precise, beyond reach. If that does not sound alarming yet, it is because it violates an assumption so firmly embedded in how we think about science that most people have never had cause to examine it. The assumption is this, that understanding a system means knowing its rules, and that once you know the rules, prediction is a matter of arithmetic. Find the law, and the future follows. It is the promise physics made in the 17th century and has been cashing ever since. Newton found the law of gravitation, and suddenly we could say where Saturn would be in 1,000 years. Maxwell found the laws of electromagnetism, and we could design radio. Schrödinger found the equation for the quantum world, and chemistry became calculable. The rule, then the outcome. That is how it is supposed to work. Turbulence is where that stops, not at the edge of the observable universe, not at energies we cannot reach, not in a regime where the equations might be incomplete. Here, in a medium you can put your hand into, governed by a law that fits comfortably on one line and that nobody disputes, the outcome is inaccessible. The rules are fully known, and the behavior is not. There is a remark I want to introduce now, because it is going to come back at the very end of tonight and mean something different when it does. In 1932, at a meeting of the British Association in London, a physicist named Horace Lamb stood up to speak. Lamb was then in his 80s. He had written the standard textbook on fluid mechanics, a book so thorough that it was still being reprinted a century later, and he had spent essentially his entire working life on the motion of fluids. He is reputed to have said this, that he was an old man, and when he died and went to heaven, there were two matters on which he hoped for enlightenment. One was quantum electrodynamics. The other was the turbulent motion of fluids. And about the first, he added, he was really rather optimistic. Hold that. The man who wrote the book on fluids expected to have a better shot at understanding the quantum behavior of light and matter than at understanding water. So why does it break? What is it about a fluid, specifically, that turns a solved law into an unsolvable problem? The answer sits inside one term of the equation, and it is worth understanding precisely, because everything difficult about turbulence descends from it. When a parcel of fluid moves, it does not move through a stationary background. It moves through other fluid, which is itself moving, and which carries the parcel along as it goes. So the rate at which conditions change at any given point depends on the velocity of the fluid at that point, multiplied by the rate at which velocity is changing from place to place. The velocity appears twice, multiplied by itself. That is called non-linearity, and it sounds like a piece of technical vocabulary. What it means physically is that the flow acts on itself. The fluid is not being pushed around by something external whose behavior you can specify in advance. It is pushing itself around. Every swirl distorts the conditions that produced it and creates new conditions that produce new swirls. You cannot break the problem into pieces, solve the pieces, and add them up, because the pieces interfere with each other. In a linear system, two solutions added together give you another solution, which is why you can analyze a radio signal by splitting it into frequencies, or a structure by adding up the loads. In a nonlinear system, that trick simply does not work. There is no decomposition. The thing has to be taken whole. And a fluid taken whole, at any real speed, contains an enormous number of interacting scales. Which brings us to the first person who managed to say something exact about when order gives way, and to a single number, still used every day, that decides the fate of every flow on Earth. The first person to catch the moment of collapse and measure it was working in Manchester, at night, because the daytime traffic shook his building. Osborne Reynolds was Professor of Engineering at Owens College, which would later become the University of Manchester, and in 1883 he published a paper that turned turbulence from something everyone had noticed into something that could be studied. His apparatus was almost embarrassingly simple: a large tank of water, a horizontal glass pipe running out of one side of it, and a fine nozzle at the mouth of the pipe, injecting a thin thread of coloured dye into the water as it entered. Picture the room. The tank has to sit undisturbed for hours before each run, because any residual swirl left over from filling it will ruin the experiment. He fills it and waits. The gaslight is low. Outside, the road is finally quiet, which matters more than it should. The vibration of carts passing during the day is enough to spoil the result, so the serious work happens late. When the water has gone entirely still, he opens the valve at the far end of the pipe, a fraction of a turn, and lets the water begin to move. The dye comes out of the nozzle and draws a line. Not a plume, not a cloud, a line. It runs the entire length of the glass pipe, a coloured wire suspended in clear water, holding its position, holding its thickness, arriving at the far end as narrow as it started. The water is moving. The dye is not spreading. Every layer of the fluid is sliding past its neighbours without exchanging anything at all. He opens the valve further. The line holds. Further. The line holds, quivers, holds. And then he opens it one more fraction, and partway down the pipe the thread detonates. There is no other word for what it looks like. The filament travels a certain distance, perfectly intact, and then bursts outward into curls and eddies that fill the whole cross-section of the pipe within a few centimetres, and downstream of that point, the water is uniformly coloured, order at one end of the glass, chaos at the other, and a boundary between them that he can watch and mark and measure. Reynolds then did the thing that made him important rather than merely observant. He varied everything. He changed the speed of the water. He changed the diameter of the pipe. He changed the temperature, which changes the viscosity, and he found that the breakdown did not depend on any of those things individually. It depended on one combination of them. Take the average speed of the flow. Multiply it by the diameter of the pipe. Divide by the kinematic viscosity of the fluid. What comes out is a pure number with no units attached. The meters and the seconds all cancel, and that number, and only that number, determines whether the flow stays smooth. We call it the Reynolds number now, and it is probably the most consequential number in engineering. What it measures, physically, is a competition. The top of the fraction represents inertia, the tendency of moving fluid to keep moving, to carry its momentum forward, to tumble and overshoot. The bottom represents viscosity, the internal stickiness that smears differences out, that drags fast fluid back and pulls slow fluid along, that flattens disturbances before they can grow. Every flow in the universe is a contest between those two tendencies, and the Reynolds number is the score. Because the Reynolds number has no units, it lets you compare things that have no business being compared, and this is where it becomes something more than an engineering convenience. It is a universal ruler for how a fluid feels to whatever is moving through it. A bacterium swimming in water lives at a Reynolds number of around 100,000th. At that value, viscosity is overwhelming, and inertia is essentially absent, and the consequences are difficult to imagine from inside a human body. If a swimming bacterium stops beating its flagellum, it does not coast. It stops within a fraction of the width of an atom, effectively instantaneously. There is no gliding, no momentum, no drifting. Water at that scale behaves less like water and more like setting concrete. A bacterium cannot swim by pushing water backwards the way you do in a pool, because the water it pushes does not go anywhere. It has to corkscrew its way forward instead, which is precisely what a flagellum does. You, swimming, are at a Reynolds number of a few 100,000. You push off the wall and you glide. A trout is at around 1,000,000. A commercial airliner in cruise, measured along its fuselage, is at a Reynolds number on the order of 100 million. At that value, viscosity has been comprehensively defeated everywhere except in a thin skin of air clinging to the surface. And inside that skin, which is a few centimetres thick, the entire drama plays out. The atmosphere of the Earth as a whole runs at a Reynolds number in the region of 100 million. There is no meaningful sense in which the weather could ever be smooth. When viscosity wins, you get the glass rod. When inertia wins, you get the churning rope. The value at which the balance tips, in a pipe, is usually quoted as 2,300. And I want to tell you what is wrong with that number, because it is the first sign that this problem is not going to behave. The figure of 2,300 does not appear in Reynolds' work. The data in his 1883 paper actually point to something closer to 2020. In a later paper, in 1895, he quoted a range of roughly 1,900 to 2,000. The value that ended up in every textbook got there largely by being repeated, which is a thing that happens more often in science than anyone likes to admit. But the real problem is deeper than a disagreement in the third digit. Reynolds could not find a unique critical value at all. He kept getting different answers, and he worked out why. The transition is exquisitely sensitive to disturbance. The exact shape of the pipe inlet mattered. Vibration in the building mattered. Residual motion in the tank mattered. When he took extraordinary care to eliminate all of it, smoothing the entry, letting the water settle for longer, isolating the apparatus from shocks, he could hold the flow laminar up to a Reynolds number of about 12,800, more than 5 times the supposed critical value. The flow that should have collapsed simply did not, because nothing had nudged it. Think about what that means. The threshold is not a property of the fluid. It is a property of the fluid and its history and everything that has happened near it. A flow at a Reynolds number of 5,000 may be smooth or chaotic, depending on whether someone walked past. There is one more thing Reynolds did that we will need much later, and I want to plant it now rather than surprise you with it. In that same 1895 paper, he asked a reasonable question. If the detailed motion is hopeless, Why not just work with averages? Do not track every eddy. Split the velocity at each point into a steady average plus a fluctuating part. Average the whole equation over time and see what you get for the mean flow. It is exactly the right instinct, and it fails in a specific and beautiful way that we will come back to. Reynolds found it himself, and he understood what he had found. When you average the equations, the nonlinear term does not politely disappear. It leaves behind a residue, the average of the fluctuations multiplied by themselves, which is a brand new quantity that your averaged equation does not tell you how to calculate. You set out to reduce the number of unknowns, and you increased it. He put his finger on that in the 1890s, and he named the leftover quantity, and it still carries his name today. Nobody has resolved it since. Every turbulence model in commercial use, in every engineering package sold anywhere in the world, exists because that residue cannot be calculated and has to be guessed at instead. Modern experiments have made this precise, and if anything, stranger. In a carefully controlled pipe, at moderate Reynolds numbers, turbulence does not appear everywhere at once. It appears in localized patches, traveling slugs of chaos, called puffs, each perhaps 20 pipe diameters long, moving downstream with laminar water in front of them and laminar water behind. A single puff is a self-sustaining pocket of disorder drifting through order, and whether any given puff survives is a matter of chance. A puff can simply decay, the chaos runs out of energy, and the water goes smooth again. Or it can split, seeding a second puff downstream, which can split again. Below a certain Reynolds number, decay wins on average, and turbulence always eventually dies. Above it, splitting wins and turbulence eventually fills the pipe. In between there is a regime where the outcome is genuinely probabilistic, and the characteristic lifetime of a puff grows not exponentially, but super exponentially, with the Reynolds number, which is a rate of increase so steep that it becomes indistinguishable from permanence over any timescale you could actually watch. So the first exact thing anyone ever established about turbulence, the critical Reynolds number, the clean threshold, the number in the textbook, turns out on inspection to be a statistical statement about a probabilistic event whose value depends on how quiet the room is. That is the pattern to watch for tonight, because it repeats. Every time someone gets a firm grip on this problem, the grip turns out to be on something softer than it looked. Reynolds gave us the conditions under which order collapses. He did not, and could not, tell us what the chaos on the other side actually does. For that, somebody was going to have to describe the inside of the mess, and the man who managed it first did most of his thinking while driving an ambulance through a war. The man who first described what is actually happening inside the chaos was a Quaker pacifist who spent the First World War driving an ambulance in France, and who did his most important thinking on the mathematics of weather between trips to the front. Lewis Fry Richardson was a meteorologist, a mathematician, and a man whose life is one of the more moving stories in the history of science. He was a Quaker, and when the war came he refused to fight, joining the Friends ambulance unit instead. He drove wounded men out of the fighting in northern France, and in the hours between, in billets and rest periods, he worked on an idea that nobody had ever attempted, predicting the weather by calculation. Everyone before him had forecast the weather by pattern matching. You look at today's chart, you find a day in the historical record that resembles it, and you say that tomorrow will probably resemble what followed. Richardson's idea was to throw all of that away and simply solve the physics. Divide the atmosphere into a grid of boxes. In each box, write down the pressure, the temperature, the humidity, the wind. Apply the equations of fluid motion, the same Navier-Stokes equations, adapted for a rotating planet and a compressible gas, to work out how each box will change over a short interval. Step forward, repeat. It is, in outline, exactly how every weather forecast on Earth is made today. He worked it out by hand, in a war, 100 years before anyone could actually do it. His trial calculation covered a single 6-hour forecast over Central Europe. It took him roughly 6 weeks of continuous arithmetic, working with a slide rule and a table of logarithms, and the result was catastrophically wrong. His forecast called for a pressure change of 145 millibars in 6 hours, a value never observed anywhere in the atmosphere, ever, by anyone. It was not a small error. It was a physically impossible answer. The method was right. What was wrong was subtler. His initial data contained small inconsistencies that the calculation amplified into nonsense, and his time step was too long for the grid he was using. Both problems were only properly understood decades later. He published the whole thing anyway, in 1922, in a book called Weather Prediction by Numerical Process, including the failure, in full, with the working shown. And in that book he did 2 things that outlived everything else in it. The first was to imagine what it would take to do the job properly. He calculated that to keep pace with the weather, to compute the future faster than it arrived, would require roughly 64,000 people calculating simultaneously. And then, rather than leaving it as a number, he described the building. He imagined an enormous hall in the shape of a sphere, its interior walls painted with a map of the whole Earth. The ceiling is the Arctic, the gallery is the tropics, England is somewhere in a balcony. In each region of the map sit the human computers responsible for that patch of the planet's atmosphere, thousands of them at their desks, each one working on the equations for their own small box of sky. In the center of the hall stands a tall pillar, and on it, like a conductor, a man directing the whole calculation. He keeps the regions in step by shining beams of colored light, rose on the areas running ahead, blue on the areas lagging behind, so that the arithmetic advances uniformly across the globe. Messengers carry results between sectors. In the basement, a research department works on improvements. Outside, Richardson notes, there are playing fields and a sports ground, because the people doing this work will need somewhere to rest. He is describing a supercomputer. He is describing it in 1922, staffed by human beings, with the parallel architecture and the synchronization problem and the memory hierarchy all worked out, decades before an electronic computer existed. It is one of the great acts of imagination in the history of the subject. His own estimate of 64,000 people was, we now know, wildly optimistic. Working through the arithmetic with modern knowledge of what a stable calculation actually requires, the real figure, to keep pace with the atmosphere by hand, would have run into the millions. The hall would have had to be a city. There is a coda to Richardson's life that I think about often. After the war, he continued in meteorology until he discovered that the Meteorological Office had been absorbed into the Air Ministry, and that his work on how gases disperse in the lower atmosphere, work he had done to understand the movement of air over farmland, was of considerable interest to people designing chemical weapons. He was a Quaker. He destroyed research rather than let it be used that way, resigned, and spent much of the rest of his working life applying mathematics to a different question entirely, the statistical causes of war. He wrote about the relationship between the length of a nation's borders and its likelihood of going to war, and in the course of that work he noticed something odd about how the measured length of a coastline depends on the length of your ruler, an observation that Benoit Mandelbrot would later credit as the seed of fractal geometry. The man who described the cascade of scales in turbulence also, almost by accident, discovered that coastlines have no definite length. Both discoveries are the same discovery, in a sense, structure that keeps going no matter how far in you look. The second thing he did in that book takes up 4 lines and is the reason his name comes up in every turbulence lecture ever given. He wrote a small piece of verse, a parody of a rhyme by Jonathan Swift, about fleas. Big whorls have little whorls that feed on their velocity. and little whorls have lesser whorls, and so on to viscosity. That is the energy cascade, and it is the central mechanism of turbulence. Let me unpack it slowly, because if you understand this, you understand why the problem is hard. Energy enters a turbulent flow at the largest scale available. For a storm, that scale is the size of the storm system, hundreds of kilometers across. For water in a pipe, it is the diameter of the pipe. For the air over a wing, it is the thickness of the boundary layer. Something is stirring the fluid at that scale. The sun heating the ground, a pump pushing water, the wing moving through air. Now, at that large scale, viscosity is essentially irrelevant. The Reynolds number is enormous, which is exactly what it means for inertia to dominate. So the energy cannot be dissipated where it enters. It has nowhere to go as heat. But the large eddy is unstable. It stretches, folds, and breaks into smaller eddies, and in doing so, it hands almost all of its energy down to them. Those smaller eddies are also at a Reynolds number too high for viscosity to matter. So they too are unstable, and they break, and they hand the energy down again. This continues, not once, not twice, but through a long chain of scales, energy passing downward, essentially without loss, each generation smaller than the last, and it continues until the eddies become small enough that the local Reynolds number finally falls to around 1, the point where viscosity is at last a match for inertia. There, and only there, the motion is finally converted into heat. That final scale has a name we will meet properly in a moment. In the atmosphere, it is around 1 millimeter. In a glass of stirred water, it is smaller than that. In the ocean, it is around 1 centimetre. Wherever you look, the bottom of the cascade is a scale you could see with your eyes if you knew where to look, and the top is a scale you would need a satellite to photograph. So consider what a thunderstorm actually is, structurally. Energy goes in at a scale of tens of kilometers and comes out as heat at a scale of 1 millimeter. Between those 2 points, there are something like 7 orders of magnitude, 7 factors of 10, of actively participating scales, all of them exchanging energy with their neighbors, all of them coupled, all of them evolving at once. That is the reason you cannot simulate turbulence by being clever about the big picture. There is no big picture that is independent of the small picture. The largest swirl in the storm is connected, by an unbroken chain, to a swirl the size of a grain of rice, and the chain carries influence in both directions. Richardson gave us the shape of the mess. What he did not give us, what nobody had, was any quantitative law describing it. How much energy sits at each scale? Is there a rule? For 19 years there was no answer, and then a Russian mathematician, working in the middle of a different war, found one, and it remains the single most successful thing anyone has ever proved about turbulence. It is also, on close inspection, not quite true. In 1941, in Moscow, with the German army approaching the city, Andrei Kolmogorov published 3 short papers that contain the closest thing turbulence has ever had to a fundamental theory. Kolmogorov was arguably the greatest mathematician of the 20th century, and certainly the greatest probabilist. He had already, at the age of 30, put the entire theory of probability on a rigorous axiomatic footing, which is a bit like putting arithmetic on a rigorous footing. Everybody had been using it successfully for centuries without anyone having established what it actually was. He worked on topology, on turbulence, on algorithmic complexity, on the mathematics of ballistics during the war, and he came at the turbulence problem with an insight that was essentially a decision to give up on the right thing. Everyone before him had been trying, in one way or another, to predict the flow. Kolmogorov stopped trying. He accepted that the detailed motion was hopeless, and asked a different question. Never mind where each eddy is. What must be true of them on average? And then he made an assumption so bold that it took decades for people to appreciate how much work it was doing. He proposed that at scales far below the size where energy enters the flow, and far above the size where viscosity destroys it, in the middle of Richardson's cascade, in what he called the inertial subrange, the turbulence forgets where it came from. Consider what that claims. A swirl of a given size in the wake of a bridge pier, a swirl of the same size in a jet engine exhaust, a swirl of the same size in the atmosphere over a wheat field, and a swirl of the same size in a stirred bathtub, should all be statistically identical, once you account for how much energy is flowing through the cascade. The stirring at the top does not matter. The geometry does not matter. The fluid does not matter. Down in the middle of the cascade, all turbulence is the same turbulence. That is a claim of universality, and universality is the most valuable thing a physicist can find. It is what makes thermodynamics work, regardless of what a gas is made of. It is what makes phase transitions in wildly different materials share the same mathematics. From that assumption, plus dimensional analysis, the technique of asking what combination of the available quantities could possibly have the right units, Kolmogorov derived a prediction. If you measure how much of a turbulent flow's energy sits in eddies of each size, and you plot it, the curve should follow a power law. Specifically, the energy should fall off as the size of the eddy shrinks, with an exponent of -5/3. -5/3. Not a number anyone would have guessed. Not 1, not 2, not a half. 5/3, arrived at by pure reasoning about what units are available, from a man who never did a fluid experiment in his life. And when people went and measured it, it was there. The 5/3 law has been confirmed in wind tunnels, in tidal channels, in the wake of aircraft, in pipe flow, in the atmospheric boundary layer above the open ocean, in the solar wind streaming past spacecraft, and in the turbulent gas between the stars. It holds across ranges of scale and energy that differ by many orders of magnitude. It is one of the most successfully tested results in all of classical physics, and it came out of 3 pages of reasoning written in a besieged city. Kolmogorov also gave us the bottom of the cascade, precisely. He worked out the size at which viscosity finally takes over, from nothing more than the rate at which energy is flowing down the chain and the viscosity of the fluid. That size is now called the Kolmogorov microscale, and it is the smallest structure that exists in a turbulent flow. Below it, nothing happens. Viscosity has smoothed everything out. And from that he gave us the single most important number in this entire story, though it would take another 50 years, and the invention of the computer, for anyone to feel its full weight. The ratio between the largest eddy in a flow and the smallest, the number of active scales stacked inside a single turbulent motion, grows as the Reynolds number raised to the 3/4 power. That is an innocent-looking statement, and it is the reason turbulence bankrupts computers. Make a flow 10 times more vigorous, and you have not made the problem 10 times harder. You have added new scales at the bottom that were not there before, and you have to resolve every one of them in all 3 dimensions, and you have to take smaller time steps to do it. We will come back to exactly what that costs. For now, hold the shape of it. The more turbulent a flow becomes, the more separate scales of motion it contains, and every one of them matters to all the others. There is a detail I like here. Kolmogorov's papers were published in Russian, in the Proceedings of the Soviet Academy of Sciences, at the height of a war that made scientific communication nearly impossible. The West did not know about them, and so, independently, over the following few years, essentially the same result was reached by 3 other people: Lars Onsager in America, Carl Friedrich von Weizsäcker in Germany, and Werner Heisenberg, yes, that Heisenberg, who worked on turbulence during and after the war. 4 of the best minds of the century, cut off from one another by the largest conflict in human history, found the same law. When that happens, it usually means you have found something real. So, we have a universal law. Surely, that is the beginning of the answer. It is not, and the reason it is not is one of the quietest disappointments in physics. The 5/3 law is not quite right. The deviations are small, and they are systematic, and they have been measured with increasing precision for 60 years. If you look only at the simplest statistic, the energy at each scale, the agreement is very good. But turbulence has more statistics than that. You can ask about the typical difference in velocity between 2 points separated by a given distance, and then you can ask about the square of that difference, and the cube, and the fourth power, and so on. Kolmogorov's theory predicts exactly what each of these should be, and as you go to higher powers, the measured values drift further and further from the prediction, in a consistent direction, every time, in every experiment. The cause has a name: intermittency. Kolmogorov's argument quietly assumed that the energy cascading down through the scales is spread more or less evenly through the fluid. It is not. Turbulent dissipation is concentrated in thin, sparse, extremely violent structures, sheets and filaments, and tubes of intense vorticity that occupy a tiny fraction of the total volume and account for a large fraction of the total activity. Most of the fluid, most of the time, is comparatively quiet. The action is in a small, wandering, fractal subset of the space. Kolmogorov himself recognized the problem and published a revised theory in 1962, incorporating a correction for the uneven distribution of dissipation. The revised theory is also not quite right. Here is where we actually stand. More than 80 years after those 3 papers, the scaling exponents of turbulence, the numbers describing how each statistical quantity varies with scale, are known to considerable precision. They have been measured in laboratories and in the atmosphere and in enormous computer simulations. They are among the best determined quantities in classical fluid mechanics. And not one of them, beyond the simplest, has ever been derived from the Navier-Stokes equations. Not one. We know the numbers because we measured them. We cannot get them out of the theory. Sit with that for a second. We have a law of nature. We have measured, to several decimal places, a set of numbers that the law must produce, and we cannot start from the law and arrive at the numbers. In any other part of physics, that situation would be regarded as a crisis. In turbulence, it is simply Tuesday. So Reynolds told us when order collapses and could not pin the threshold down. Richardson told us the shape of the collapse and could not quantify it. Kolmogorov quantified it, and the quantification is approximate for reasons nobody can derive. Each of them got a real, durable grip on this thing, and each grip turned out to be on something that gave slightly when squeezed. But so far, everything we have looked at is about the difficulty of describing turbulence. What comes next is worse. Because in 1961, a meteorologist in Massachusetts typed 3 digits into a computer, went to get a cup of coffee, and came back to a discovery that says the difficulty is not in our description at all, it is in the thing itself. Edward Lorenz was not looking for anything. He was rerunning a calculation he had already done. It was the winter of 1961, at the Massachusetts Institute of Technology, and Lorenz was a meteorologist with a mathematician's training and an interest in whether the atmosphere could be modeled by something small enough to compute. The machine available to him was a Royal McBee LGP-30, a vacuum tube computer about the size of a desk, with a memory built from a rotating magnetic drum. It could perform roughly 60 multiplications a second. Your phone is somewhere in the region of 100 billion times faster. Lorenz had a simplified model of the atmosphere running on it, 12 equations describing a crude version of how air circulates when it is heated from below. He would set it going, and it would print, line by line, a sequence of numbers describing an imaginary weather that unfolded at roughly 1 simulated day per minute of real time. He had been watching these artificial weathers for months, looking for patterns. On this particular day, he wanted to look more closely at a stretch of a run he had already completed. Rather than start from the beginning, he decided to restart the calculation from a point in the middle. He took the printout from the previous run, read off the numbers at that point, typed them in, and set the machine going again. Then he walked down the hall to get a cup of coffee. He came back an hour later, an hour of machine time, which was 2 months of simulated weather, and looked at the new printout beside the old one. At the start, the 2 runs agreed, as they should. A little further on, they agreed to most decimal places. Further on still, small differences, and then the 2 weathers separated completely. By the end of the run, there was no relationship between them at all. One had a storm, where the other had clear conditions. They were not the same weather. They were not even similar weather. His first assumption was a hardware fault, which was reasonable. Vacuum tubes failed constantly. But there was no fault. The machine had done exactly what it was told, both times. The explanation, when he found it, was almost too small to be an explanation. The computer held 6 decimal places internally, but printed only 3, to save paper and time. When Lorenz read the number off the printout, he had typed 0.506. The machine's internal value had been 0.506127, a difference of about 1 part in 4,000. In meteorological terms, a difference far smaller than any real measurement error, smaller than the accuracy of any thermometer, any barometer, any wind gauge that has ever existed. A difference that, in every other branch of science Lorenz knew, would have been utterly negligible. That difference ate the forecast. His 1963 paper, called Deterministic Non-Periodic Flow, is one of the most cited papers in the physical sciences, and its title is the whole argument compressed into 3 words. Deterministic. There is no randomness anywhere in these equations. Feed in identical numbers, and you will get identical results, every time, forever. Non-periodic. And yet the behavior never repeats, never settles, never falls into a cycle you could extrapolate. Those 2 properties together are the discovery. A system can be perfectly deterministic and practically unpredictable at the same time, not because we do not know the rules, we wrote the rules, but because any uncertainty in the starting conditions, however small, grows exponentially until it swamps everything. And there is always uncertainty in the starting conditions. There is no such thing as a measurement with infinite precision. Lorenz reduced his 12 equations to 3 to see if the effect survived, and it did. 3 equations, 2 nonlinear terms, and a solution that traces out the shape now printed on 1,000 physics department t-shirts. A trajectory that loops around one lobe some number of times, crosses over, loops around the other, crosses back, and never once passes through a point it has visited before, forever, in a bounded region of space. There is a practical consequence of Lorenz's result that you have almost certainly seen without recognizing what it is. When a forecast tells you there is a 40% chance of rain on Thursday, that number is not a hedge, and it is not a marketing decision. It is a measurement of chaos. Modern forecasting centers do not run their model once. They run it dozens of times, 50, 100, each time from very slightly different starting conditions, perturbed within the range of genuine observational uncertainty. Then, they look at what comes out. If all 100 runs agree, the forecast is confident, and the atmosphere happens to be in a state where small errors are not growing quickly. If the 100 runs disagree wildly, with some producing a storm and others producing sunshine, the forecast is uncertain, and the atmosphere is in a state where small errors are exploding. The percentage you are given is literally the fraction of those runs that produced rain. The weather forecast is an instrument for measuring how unpredictable the weather currently is. Every probability you have ever been given about the sky is a chaos measurement, made by running the same physics over and over, and watching how fast the copies drift apart from each other. That is what Lorenz's coffee break turned into. Now I want to correct something, because it is repeated everywhere, and it is not true. The famous 2-week limit on weather forecasting is not from Lorenz. It is not in the 1963 paper. It comes from a report published in 1966 by a panel chaired by Jule Charney, one of the founders of modern numerical weather prediction. Charney's group looked at how quickly errors grew in the first generation of general circulation models and found a doubling time of about 5 days. If a realistic observational error doubles every 5 days, then starting from the precision actually achievable in the 1960s, it takes roughly 2 weeks for the error to grow as large as the weather itself, at which point the forecast contains no information. Lorenz supplied the mechanism. Charney's group supplied the number. The two get conflated constantly. The butterfly came later still. In 1972, Lorenz was scheduled to give a talk and had not submitted a title, so the session organizer wrote one for him. Predictability. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? Lorenz had used a seagull in an earlier version. The most famous metaphor in the history of chaos theory was chosen by an administrator against a deadline. Now, the thing that I find genuinely difficult about the 2-week limit is how well it has held up. Consider what has happened since 1966. Computing power has increased by something on the order of 1 trillion-fold. We have put weather satellites in orbit, and they measure temperature and humidity through the depth of the atmosphere over the entire planet, several times a day. We have thousands of automated buoys, aircraft reporting continuously, radiosondes, radar networks. We have developed data assimilation techniques of extraordinary sophistication, which blend observations with model states in a statistically optimal way. The models themselves have gone from a handful of layers to over 100, with grid cells measured in single kilometers. It is worth being precise about what exponential error growth actually means, because the word exponential gets used loosely. If the error doubles every 5 days, then improving your initial measurements by a factor of 2 buys you 5 extra days of forecast. Improving them by a factor of 1,000 buys you about 50 days, which sounds encouraging until you consider that 1,000-fold improvement in measuring the global atmosphere is not an engineering program, it is a fantasy. And even that would eventually run into the fact that the atmosphere contains structures below any observable scale, which grow upward and contaminate the large scales from below. The error does not only come from imprecise measurement, it comes from the parts of the sky nobody is measuring at all, because they are the size of a room. All of that has produced enormous, genuine improvement. A 5-day forecast today is about as reliable as a 1-day forecast was in the 1980s. That is a real achievement that saves lives every hurricane season. And the horizon has barely moved. 60 years, 1 trillion-fold increase in computing power, and complete observation of the planet from orbit, and we have pushed the wall out by a few days at most. Recent work with machine learning weather models has started to probe whether some large-scale patterns carry useful information a little beyond the classical boundary, and the results are interesting. But nothing suggests the wall is going away. It is not a limit on our instruments. It is a property of the atmosphere. Let me stop and stack up what we have, because we are about halfway through, and the pieces matter. We have an equation that is correct, and that nobody disputes. We have a number, from Reynolds, that tells us when smooth flow will collapse, except that the number is not fixed and depends on how quiet the room is. We have a picture, from Richardson, of energy cascading down through a chain of scales spanning many orders of magnitude. We have a law, from Kolmogorov, that tells us how energy is distributed among those scales, except that it is systematically slightly wrong, for reasons nobody can derive. And now we have a result, from Lorenz, that says that even with a perfect equation, and a perfect law, prediction has a hard ceiling built into the physics itself. That is 140 years of first-rate work, and every piece of it is real, and none of it constitutes a solution. Which raises a question I have been putting off, and cannot put off any longer. What would solving this even look like? What is it, exactly, that we are failing to do? The answer turns out to be more humiliating than you might expect. The word solved is doing a great deal of hidden work, and turbulence fails in 4 separate senses of it at once. I want to go through them one at a time, because the confusion around this problem almost always comes from someone using one meaning while somebody else uses another. And the fourth one is where the $1 million is. The first sense is analytic solution. This is what most people picture, a formula. You want an expression that takes the position, the time, and the starting conditions, and returns the velocity of the fluid. Write it down, plug in numbers, get an answer. For fluid flow, analytic solutions do exist, for a small handful of idealized situations. Steady flow down a straight circular pipe has one. It is a neat parabola of velocity, fastest in the middle, 0 at the walls. Flow between 2 rotating cylinders has one. The flow generated by a flat plate, suddenly jerked into motion, has one. There are perhaps a couple of dozen exact solutions in the whole of fluid mechanics, and every single one of them describes a smooth, orderly, laminar flow. There is not one for any turbulent flow, and the situation is worse than merely not having found one. There is good reason to believe no such expression exists, that a turbulent flow is not the kind of object that can be written as a formula, in the same way that the digits of an irrational number cannot be written as a repeating pattern. The flow contains too much independent structure. There is nothing to compress it into. The second sense is statistical closure, and this is the one that will make you understand why the problem is genuinely mathematical rather than merely complicated. The reasoning goes like this. If we cannot track every eddy, fine. Nobody wanted to know the position of every eddy anyway. What an engineer wants is the average velocity profile in the pipe, the average drag on the wing, the average heat transferred by the flow. So take the Navier-Stokes equations and average them over time. Every fluctuating quantity becomes a steady average plus a wiggle, and when you average, the wiggles ought to cancel. Most of them do, but the non-linear term is a product, velocity multiplied by velocity, and the average of a product is not the product of the averages. When you work it through, you are left with an extra quantity, the average of the fluctuation multiplied by the fluctuation. It behaves like a stress in the equation, and it is called the Reynolds stress, after the man in Manchester who found it in the 1890s. So now you have an equation for the mean flow that contains an unknown. Fine, you think. Derive an equation for the Reynolds stress. You can, and when you do, that equation contains the average of a triple product, 3 fluctuations multiplied together, which is a new unknown. So derive an equation for that. It contains a quadruple product. This does not stop. It never stops. Every level of the hierarchy generates an unknown one level higher, forever. There is no point at which the system closes. This is called the closure problem, and it is not a failure of technique. It is a direct, unavoidable consequence of the nonlinearity in the original equation. It has been attacked continuously since the 1890s by extremely capable people, and it has never been solved, only papered over with approximations. It is worth dwelling on how strange that hierarchy is, because it has no real parallel elsewhere in physics. In most subjects, averaging is how you make things easier. You cannot track every molecule in a gas, so you average, and out comes thermodynamics, temperature, pressure, entropy, a clean, closed, spectacularly successful theory that tells you everything you need without knowing where any molecule is. Statistical mechanics is the great success story of exactly this move. Turbulence refuses it. Average the equations, And instead of a simpler theory, you get an infinite regress. The information you threw away does not stay thrown away. It comes back, demanding to be accounted for, at every level. There is no temperature and pressure equivalent for a turbulent flow, no small set of averaged quantities that obey their own closed laws. The reason is that in a gas, the molecules are effectively independent. They collide and forget. In turbulence, the eddies are not independent at all. Every scale is coupled to every other scale, and coupling is precisely what averaging cannot survive. Every turbulence model in the world is a piece of paper over that whole. You get to a certain level of the hierarchy, and then you guess. You write down a plausible expression for the unknown quantity in terms of things you do know. You put some adjustable constants in it, and you tune the constants until the model reproduces experiments you have already done. The most widely used engineering turbulence model in the world contains 5 such constants. Their values were fixed in the early 1970s by fitting to a handful of laboratory flows, and they have barely changed since. That model is currently being used to design things you will travel in. The third sense of solved is computational. Forget formulas and forget averages. Just simulate it. Put the fluid on a grid. Resolve every scale from the largest eddy down to the Kolmogorov microscale, where viscosity kills the motion, and step it forward in time. This is called direct numerical simulation, and unlike the first 2 approaches, it genuinely works. It is exact. No models, no fitted constants, no guessing. It is also, for anything at industrial scale, unaffordable in a way that no amount of technological progress will fix. We are going to spend a whole part of tonight on exactly why, because the numbers are worth seeing. And then there is the fourth sense. This is the one where $1 million is sitting, unclaimed, and it is the one that should genuinely unsettle you. On the 24th of May, in the year 2000, in Paris, the Clay Mathematics Institute announced 7 problems. The date and the place were chosen deliberately. Exactly 100 years earlier, David Hilbert had stood in Paris and presented a list of 23 problems that went on to shape mathematics for a century. The Clay Institute attached a prize of $1 million to each of its 7. The list includes the Riemann hypothesis. It includes the P versus NP problem, which asks whether every problem whose answer can be quickly checked can also be quickly solved. And it includes, sitting among the deepest questions in pure mathematics, the Navier-Stokes existence and smoothness problem. Of the 7, exactly 1 has been solved. The Poincaré conjecture, proved by Grigori Perelman, who then declined the $1 million and the Fields Medal, and withdrew from mathematics entirely. 6 remain open. Navier-Stokes is one of them. Now, here is what the Navier-Stokes problem actually asks. And I want you to brace for how small it is. It does not ask anyone to predict turbulence. It does not ask for the drag on a wing, or the exponents Kolmogorov could not derive, or a solution to the closure problem, or a weather forecast, or anything an engineer would recognize as useful. It asks this: if you start with perfectly smooth initial conditions, a fluid that is behaving nicely everywhere, with no sharp edges, no infinities, nothing pathological, do the Navier-Stokes equations continue to produce a smooth, sensible solution for all future time? Or can the solution, at some finite moment, blow up? Can some quantity in it become infinite? That is the whole question. Not what the fluid does, just whether the equations keep making sense. There is one more thing about that phrase, blow up, that deserves unpacking, because it sounds violent, and it is actually rather precise. It does not mean an explosion. It means that some quantity described by the equations, the velocity at a point, or the rate at which velocity changes from place to place, or the local spinning rate of the fluid, heads to infinity and gets there in a finite amount of time, not eventually, not asymptotically, At, say, 3.7 seconds, the mathematics says infinite. If that can happen, the equations have not merely become hard to compute, they have stopped describing anything. A physical fluid does not have infinite velocity at a point. So either the equations forbid it, and nobody can prove they do, or they permit it, in which case somewhere inside the mathematics we use to build aircraft, there is a scenario where the model produces a number that corresponds to nothing in the world, and we have no idea how close any real flow has ever come to it. The formal statement, written by Charles Pfefferman for the Clay Institute, offers 4 ways to claim the prize. Prove that smooth solutions always exist in 3-dimensional space. Or, prove it on a 3-dimensional torus, which is a mathematically convenient version with the edges wrapped around. Or prove the opposite in either setting. Construct a specific example where the equations do break down. Any one of the 4. Prove it works, or prove it fails. Nobody minds which. Nobody has done either. Let me put that in the plainest terms I can. There is a set of equations that we use every day to design the aircraft you fly in, to forecast the storms that people evacuate for, to model the blood flow in surgical planning, to build the reactors that may one day supply our power. And there is a standing offer of $1 million to anyone who can prove that those equations do not, under some circumstances we have not yet stumbled into, produce infinity. The prize is not for the answer. The prize is for permission to trust the question. We are not asking mathematics to tell us what turbulence does. We gave up on that a long time ago. We are asking it to confirm that the equations we are already relying on are not lying to us, and it will not confirm it, and it has been 26 years since the offer was made and 180 since the equations were written. So why is it so hard? Why can nobody prove something that sounds, on the face of it, like it ought to follow from basic energy accounting? The reason involves a specific piece of 3-dimensional geometry, a French mathematician who invented an entire branch of analysis as a workaround, and a proof from 2014 that demonstrated something genuinely disheartening, that most of the obvious ways of attacking the problem cannot possibly work. The entire difference between a solved problem and an unsolved one comes down to a single geometric fact about 3-dimensional space. In 2 dimensions, the Navier-Stokes problem is finished. It was settled largely through the work of Olga Ladyshenskaya in the 1950s and 60s, and the answer is the comfortable one. In a 2-dimensional fluid, smooth initial conditions produce smooth solutions forever, no blow-up, no infinities. The equations behave. Ladyshenskaya is worth a moment on her own. She was barred from graduate study at Leningrad University because her father, a mathematics teacher, had been arrested and executed as an enemy of the people in 1937. She completed her doctorate in Moscow instead, and went on to become one of the most important figures in the theory of partial differential equations in the 20th century. She proved the 2-dimensional case and spent decades on the 3-dimensional one, along with everyone else, and did not get it. So what changes when you add the 3rd dimension? Vorticity. Specifically, the ability to stretch it. Vorticity is the local spinning of a fluid. Imagine dropping a tiny paddle wheel into the flow and asking how fast it rotates. In a turbulent fluid, vorticity is not spread evenly. It concentrates into tubes and filaments, like the visible funnel of a dust devil or the twin trailing vortices that come off the wingtips of an aircraft. Now, in 3 dimensions, a vortex tube can be stretched by the surrounding flow. If the fluid around it is pulling the tube out lengthwise, the tube gets longer and thinner. And here the fluid does something you have watched 100 times without connecting it to this. It spins faster. It is the figure skater. A skater spinning with arms out pulls them in and accelerates, because angular momentum is conserved and she has reduced her radius. A vortex tube being stretched is doing exactly that. It narrows, and the spin rate climbs. So consider what that permits. A stretching vortex spins faster. A faster spinning vortex generates stronger flow around itself. Stronger flow can stretch neighboring vortices harder, which makes them spin faster, which stretches others. That is a feedback loop with no obvious ceiling, and it is the engine that could, in principle, drive a quantity to infinity in a finite time. You can watch vortex stretching happen in the world, once you know to look for it. A tornado is, in large part, a stretching event. A broad, slowly rotating column of air within a thunderstorm gets drawn upward by the updraft, and as it is pulled taller, it necks down and spins up, converting a lazy rotation kilometers across into a violent one 100 meters across. The same mechanism appears when you pull the plug in a bath and the drifting rotation of the water tightens into a funnel over the drain. It appears in the trailing vortices behind an aircraft, which is why air traffic control imposes separation distances behind heavy jets. Those tubes persist for minutes and can roll a smaller aircraft that flies into them. In every one of those cases, energy that was spread over a large region has been concentrated into a small one, and the fluid moves faster there as a direct consequence. The question the mathematicians are asking is simply whether there is anything that stops this process, whether there is a flaw. Nature appears to have one. Real tornadoes do not become infinitely fast, and the obvious candidate for the flaw is viscosity, which becomes more and more effective the smaller the structure gets. The trouble is that nobody has been able to prove viscosity always wins the race. In 2 dimensions, none of this is available. In a flat flow, vorticity points perpendicular to the plane of motion, straight out of the page, and the flow within the page cannot tilt it or stretch it. The vorticity of any parcel is simply carried along, unchanged in magnitude, and slowly smoothed by viscosity. There is no amplification mechanism at all. That is the whole difference. One geometric fact, that in 3 dimensions a spinning tube can be pulled longer, and in 2 dimensions it cannot. On one side of that fact, a theorem. On the other, 70 years of failure and $1 million. Let me lay out what has actually been proved in 3 dimensions, because the shape of the partial results tells you a great deal. In 1934, Jean Leray proved that solutions exist for all time, but he had to weaken what he meant by a solution to do it. A weak solution satisfies the equations in an averaged, integrated sense, rather than at every point. It may not be differentiable everywhere. It may have rough patches where the classical equations do not literally apply. Leray proved these always exist, forever, for any reasonable starting condition. And here is the detail I find remarkable. The concept of the weak solution, which is now absolutely fundamental across the entire theory of partial differential equations and is taught to every graduate student in the field, was invented as a workaround for turbulence. Leray could not construct proper solutions, so he redefined what a solution was. An enormous branch of modern mathematics exists because this one problem would not yield. What is known about proper, smooth solutions in 3 dimensions is this. They exist for a short time, starting from any smooth condition. You can always run the equations forward a little. They exist forever if the initial disturbance is small enough, meaning a gently disturbed fluid is safe. Neither of these helps with the real question, which is what happens to a vigorous flow over a long time. The strongest general result came in 1982 from Luis Caffarelli, Robert Kohn, and Louis Nirenberg. They proved that if singularities exist, they must be extremely sparse. The set of points in space and time where things could go wrong has, in a precise technical sense, 0 one-dimensional measure. Loosely, the bad points could not even form a curve. They would have to be scattered more thinly than that. More than 40 years later, that remains the best anyone has done. Nobody has closed the gap between extremely sparse and none. And in 2014, Terence Tao published a paper suggesting that the gap may not be closable by any method currently available. Tao is one of the strongest mathematicians alive, a Fields medalist, and someone with a reputation for going into a hard problem and coming out with something nobody expected. What he did here was not to attempt a proof. He did something more devious. He built a fake. Tao constructed a modified version of the three-dimensional Navier-Stokes equations, an averaged version, in which the way different parts of the flow interact with each other has been rearranged. Crucially, his modified system preserves every general feature that mathematicians normally use in these arguments. It has the same scaling behavior under rescaling of space and time. It obeys the same energy identity, meaning energy is conserved and dissipated in exactly the same way. It has a nonlinear term of the same size and structure. And for his fake system, he proved that a smooth solution does blow up in finite time. He built a specific example, and he showed the infinity arrives. Now think about what that implies. Suppose someone produces a proof that real Navier-Stokes solutions always stay smooth, and suppose that proof uses only the general features, the energy identity, the scaling, standard estimates on the size of the nonlinear term. That same proof would apply, word for word, to Tao's system, where the conclusion is provably false. Therefore, no such proof can exist. Tao called this the supercriticality barrier. What it means is that any successful attack on the problem must use some finer, more specific structure of the true equations, some detailed property that his averaging destroyed. And nobody knows what that property would be, or whether the true equations even have one. This is the main reason many mathematicians regard the problem as genuinely out of reach rather than merely difficult. It is not that the mountain is tall, it is that the obvious routes have been proved to be dead ends. It also explains something that happens regularly. Claimed proofs of the Navier-Stokes problem appear several times a year, on preprint servers, in the inboxes of the Clay Institute, occasionally from credentialed mathematicians. In 2014, a Kazakh mathematician named Muktarbay Otelbayev announced a proof of global regularity and briefly attracted international attention. A counterexample to one of his key lemmas was found within weeks. The failure mode is almost always the same. Translated into Tao's language, the argument turns out to be one of the abstract approaches that the barrier already rules out. Now I want to tell you Tao's own intuition for how blow-up might actually happen, because it is the strangest idea in this entire subject, and it has stayed with me since I first read it. The nonlinear term moves energy from large scales to smaller ones. That is the cascade. So suppose, and this is a thought experiment, not a claim about reality, suppose you could arrange a blob of fluid whose motion causes it to assemble, at a smaller scale, a faithful copy of itself. Same shape, same structure, carrying most of the original energy, but compressed into a smaller region, and therefore moving faster. That copy, being a faithful copy, does the same thing. It builds a smaller, faster version of itself. And that one builds another. Each generation is smaller than the last, and because each is faster, each takes less time than the last. If the times shrink quickly enough, if they form a convergent series, like a half plus a quarter plus an eighth, then after a finite total time, infinitely many generations have occurred. The structure has shrunk to a point, and the velocity has gone to infinity. Tao described the required object as something like a water computer, or a self-replicating fluid machine, an arrangement of moving liquid whose only function is to construct a smaller, faster version of itself, over and over, forever, in finite time. He has been careful to say he cannot build one in the real equations, only in his averaged caricature, and that the true equations may well forbid it, but nobody has shown that they do. The idea has spawned its own small research literature. If a fluid can be arranged to perform one specific operation, build a scaled copy of itself, then in principle, it can be arranged to perform other operations. And people have asked seriously whether the Euler or Navier-Stokes equations are capable of universal computation. Whether you could, in principle, build a general-purpose computer out of nothing but moving liquid obeying the ordinary laws of fluid motion. Work by Terence Tao, and later by others, has produced constructions in related systems that come uncomfortably close to answering yes. If that were true of the real equations, the consequences for the millennium problem would be severe. A system capable of universal computation can be asked questions that are provably undecidable, questions with no algorithmic answer, in the sense Alan Turing established in 1936. The question of whether a given flow eventually blows up could turn out to be one of them. In that scenario, the problem does not have an answer that is hard to find. It has no answer at all, and no proof either way is possible. That is a genuinely unsettling possibility, and it is taken seriously by serious people. It would mean the Clay Institute has offered $1 million for something that cannot be done. That is the state of the art. We cannot prove the equations behave. We cannot prove they misbehave. We have proved that the sensible ways of trying will not work. And the leading scenario for how it might all go wrong involves a machine made of water that builds copies of itself until it tears a hole in the description. We can write the law and still not know the outcome. 10 parts ago, that was a paradox. Now it has a precise mathematical shape, and the shape is a wall. But mathematics is not the only place this bites. And if you have been listening to all this, thinking that it is a beautiful abstract problem with no consequences for anybody who is not a mathematician, the next hour is going to change your mind. Because the bill for this unanswered question arrives every single day, and everybody pays it. There is one honest way to compute a turbulent flow, and it is priced out of the universe. It is called direct numerical simulation, and the idea is exactly what it sounds like. No models, no fitted constants, no averaging, no closure, no guessing. You lay a grid over the fluid, fine enough that the smallest structures in the flow are properly resolved, and you march the Navier-Stokes equations forward in time on that grid. If your grid is fine enough, and your time step is short enough, what comes out is the truth. It is as exact as physics gets. The question is how fine the grid has to be, and the answer is where the trouble starts. Remember Kolmogorov's result about the ratio of scales. The largest eddy in a flow, divided by the smallest, grows as the Reynolds number to the 3/4 power. Your grid has to resolve the smallest one, and it has to span the largest one, in all 3 dimensions. So the number of grid points you need goes as that ratio cubed, the Reynolds number to the 9/4 power. And then, because faster flows require shorter time steps for the calculation to remain stable, you pay again in the time direction. Put it together, and the total cost of a direct numerical simulation scales roughly as the cube of the Reynolds number. Cube, not squared, not linearly. If you want to simulate a flow that is 10 times more vigorous, it costs you 1,000 times more computation. 100 times more vigorous costs 1,000,000 times more. Now let me give you the Reynolds numbers of things you care about. A model in a laboratory water channel might sit at 10,000. That is comfortably simulable and has been for years. The air flowing over the fuselage of a medium-sized airliner at cruise is at a Reynolds number on the order of 100 million. Expressed in the form engineers use for wall-bounded flow, the friction Reynolds number over that fuselage is around 40,000. Take the ratio between the laboratory case and the aircraft, cube it, and you have the factor by which the computation grows. It is a number with a great many zeros in it. I want to give you the current state of the art, because people did try, And what they achieved is genuinely impressive, and it is still nowhere near enough. In February of 2026, a team from the Georgia Institute of Technology used Frontier, the exascale supercomputer, at Oak Ridge National Laboratory in Tennessee, one of the fastest machines that has ever existed, to run the largest direct numerical simulation of turbulence ever attempted. They resolved 35 trillion grid points. 35 trillion, roughly 4,000 grid points for every human being alive. Related exascale work has run turbulence in a cubic box, divided 32,768 ways along each edge. And that is still a box of idealized turbulence, not an aircraft. Not a wing-at cruise, not a full fuselage, not an engine, not a weather system. A cube of fluid being stirred, with periodic boundaries, in conditions chosen to be as clean as possible. We built one of the largest machines in the history of computing, and we can simulate a box. That is not a criticism of the people who did it. The science that comes out of those runs is exactly how we test whether Kolmogorov's corrections are right, and there is no other way to get it. It is simply an honest statement of where the frontier sits. Here is why the gap does not close by waiting. Computing power has, historically, roughly doubled every couple of years. Under a cubic cost law, a doubling of computing power buys you a factor of about 1.26 in Reynolds number, 26%. Every 2 years, if the exponential holds, which it is no longer reliably doing, to go from a laboratory flow to a full aircraft at cruise, you need a factor of 10,000 in Reynolds number, which is a factor of 1 trillion in computation, which at 26% per doubling is somewhere north of 40 doublings, which is 80 years of an exponential that has already begun to flatten. There is a further indignity hidden in the cost law that is easy to miss. Direct numerical simulation does not merely get expensive as the flow becomes more vigorous. It gets expensive at exactly the point where the flow becomes interesting. Low Reynolds number flows are the ones that behave, the ones where viscosity keeps order, the ones you could almost have guessed the answer to. The regime where turbulence does something you could not anticipate is, by definition, the high Reynolds number regime, and that is the regime the cost law walls off. The method is affordable precisely where it is least needed, and unaffordable precisely where it matters. Nature has arranged the difficulty and the importance to rise together. And even if you got there, you would have simulated one aircraft, at one speed, at one angle of attack, on one afternoon. Design requires thousands of such runs. Between the honest method nobody can afford and the crude method that just averages everything away, there is a compromise, and it is where most serious computational work now lives. It is called large eddy simulation, and the reasoning behind it is genuinely elegant. Kolmogorov said the small scales are universal, that down in the middle of the cascade, all turbulence looks the same regardless of what produced it. If that is true, then the small scales are the part you do not need to compute, because they are the same everywhere and can be represented by a general-purpose model. The large scales, by contrast, are the ones that depend on the specific geometry, the shape of the wing, the bend in the pipe, the layout of the city, and those you must resolve properly. So large eddy simulation resolves the big structures directly and models only what happens below the grid. It is far cheaper than resolving everything, and it is far more trustworthy than averaging everything, and it is now used routinely for combustion, for building aerodynamics, for atmospheric flows. It also inherits the problem. Near a wall, the eddies that matter shrink with the Reynolds number, so the boundary layer has to be resolved almost as finely as in a full simulation, and the boundary layer is precisely where the drag lives. Wall-resolved large eddy simulation of a full aircraft remains out of reach for the same reason everything else is. The compromise buys you a great deal in the middle of the flow and almost nothing at the surface. So what do we actually do? I want you to come with me into the place where this really matters. Take yourself up to 38,000 feet at night in the seat you would normally be dozing in, and shrink down until you can pass through the window and out onto the upper surface of the wing. The air out here is moving past at around 250 meters per second, and it is 50 degrees below zero. But right at the metal, in the last fraction of a millimeter, the air is not moving at all. It is stuck. Air molecules in contact with a solid surface do not slide along it. They cling. That is the no-slip condition, and it is one of the most consequential facts in engineering. So somewhere between the motionless film at the surface and the 250 meter per second stream, a few centimeters above it, the air has to make up all that speed. And it does so violently. Descend into that layer, and you are inside a structure that looks nothing like smooth flow. There are long streaks of slower fluid lying along the surface, alternating with streaks of faster fluid, spaced with a regularity nobody imposed. Every so often, one of those slow streaks lifts, wobbles, and bursts, throwing a plume of slow fluid up into the fast stream, while a sweep of fast fluid dives down to take its place. That exchange happens continuously, across every square centimeter of the aircraft's surface, thousands of times a second, and the smallest eddies involved are a fraction of a millimeter across. That layer is a few centimeters thick. It is responsible for about half of everything the engines are working against. And here is the point of taking you out there. Nobody can compute what you are standing in. Not at this Reynolds number, not with any machine that exists or is planned. The near-wall cycle you are watching, the streaks, the ejections, the sweeps, is understood qualitatively, has been photographed and measured and simulated at low speeds, and cannot be calculated from first principles at flight conditions. So the aircraft you are sitting on was designed with a model. Somebody wrote an approximate expression for the unknown Reynolds stresses, put adjustable constants in it, tuned those constants against wind tunnel data and previous aircraft, and used it. The model works well inside the range where it was calibrated. Outside that range it degrades, and it does not warn you when it does. This is the honest reason wind tunnels still exist. It is the 2020s, we have exascale computers, and every major aerospace manufacturer on Earth still builds physical models and blows air at them, because the simulation cannot be trusted on its own. It is also why flight test programs still find surprises, behaviors in the real aircraft that the computational model did not predict, discovered by a test pilot rather than a processor. There is a phrase that gets used in the industry for the current approach, and it is more candid than you might expect from engineers. Educated guessing, validated by experiment. That is the state of the art in a $200 billion industry, 180 years after the equations were written down. We have now seen what it costs to simulate the problem. What we have not looked at is what it costs not to solve it, and that number is a great deal larger than anyone's supercomputer budget. Every person listening to this is paying for this unsolved problem every day, and almost nobody knows it. Start with the aircraft, because the numbers there are cleanest. Roughly half of the total drag on a commercial transport aircraft in cruise is skin friction, the sheer resistance of air dragging along the surface. Depending on the aircraft and the study, the figure is quoted between 45 and 50%. Not lift-induced drag, not wave drag, not the drag of the shape pushing air aside. Just friction, generated in that thin, turbulent layer we walked out onto. And a conservative rule of thumb in the industry is that a 1% reduction in cruise drag yields about a 0.75% reduction in fuel burn. So consider what a modest improvement is worth. Global commercial aviation burns something in the region of 100 billion gallons of jet fuel a year. NASA studies in the 1980s estimated that a 10% reduction in fuselage skin friction alone would have been worth on the order of $250 million a year in fuel to the commercial fleet, and the fleet and the fuel price have grown considerably since. Across the industry today, the value of a few percent runs to billions annually, before you count the carbon. It is worth understanding why that friction is so stubborn, because the instinct is always to make things smoother, and smoothness is not the answer. If the air over a wing flowed in neat parallel layers, the friction would be a fraction of what it actually is. In laminar flow, the only thing transferring momentum between one layer and the next is molecular viscosity, which is feeble. But in turbulent flow, whole parcels of fluid are being physically thrown between layers. A slow parcel from near the surface hurled up into the fast stream, a fast parcel driven down to the wall. Each of those exchanges transfers far more momentum than molecular diffusion ever could, and the sum of them is the drag. So turbulence is not friction made worse. It is a completely different and far more effective mechanism for the same thing. Turning a laminar boundary layer turbulent can increase skin friction by a factor of 5 or more, which raises the obvious question, why not keep it laminar? People have tried for 80 years, and the answer is the sensitivity Reynolds found in Manchester. The boundary layer on a real wing, in real air, encountering real insects and real surface imperfections, and real acoustic vibration from the engines, will trip. Laminar flow control systems that actively suck air through microscopic holes in the wing surface to stabilize the layer have been flown experimentally and do work. They are also heavy, complex, prone to clogging, and expensive to maintain, and the industry has never been able to make the arithmetic close. Now here is the part that makes it a turbulent story rather than an engineering story. We know, roughly, how to get some of it. If you look at the skin of a fast-swimming shark under magnification, it is not smooth. It is covered in tiny tooth-like scales called denticles, ribbed lengthwise, running with the flow. Those ribs interfere with the near-wall structures in the boundary layer, the streaks and the sweeps you stood among a few minutes ago, and they push the most violent activity slightly further from the surface. The result is less friction, not more, which is counterintuitive enough that when it was first proposed, people did not believe it. Adding roughness reduces drag if the roughness has the right shape at the right scale. Engineered versions are called riblets. In the laboratory, they deliver drag reductions of the order of 5 to 10%. In actual service, a riblet film applied to Airbus A340-300s, flown by Cathay Pacific, produced skin friction reductions in the region of 5 to 8%. That works. And the design of it remains largely empirical. You make riblets of various sizes, you test them, you keep the ones that work. Because the near-wall cycle they are interfering with cannot be computed from first principles at flight conditions, nobody can derive the optimal riblet from theory. A solved turbulence problem would let you design that surface exactly, and the same reasoning applies to every surface that moves through a fluid. Now the atmosphere, where the stakes stop being financial. Every climate model on Earth divides the atmosphere into grid cells. The best of them, run on the largest machines, use cells of a few kilometers. Most operate coarser than that. Everything smaller than a grid cell is invisible to the model, and a very great deal happens below that scale. Every individual cumulus cloud, every turbulent eddy carrying heat and moisture upward from the surface, every breaking gravity wave, every plume of rising air over a warm field. These processes are not incidental. Collectively, they move a large fraction of the heat and water that drives the whole system. Since the model cannot see them, they have to be parameterized. A parameterization is a formula that estimates the aggregate effect of the invisible processes from the variables the model does track. It is not derived from the Navier-Stokes equations, because that derivation is the closure problem and nobody can do it. It is constructed from physical reasoning, fitted to observations, and tuned. And cloud and convection parameterization is, by broad agreement, the single largest source of disagreement between climate models. When you ask how much the planet warms for a doubling of carbon dioxide, and different models give you different answers, the dominant reason is not their treatment of the oceans, or the ice, or the carbon cycle. It is how each one handles small-scale turbulent convection in clouds. There is a phrase for the situation modelers now find themselves in, and it captures the awkwardness perfectly: the grey zone. As computers improve, model grids get finer, and eventually, the grid spacing approaches the actual size of the convective structures being parameterized. At that point, the turbulence is neither properly resolved nor validly parameterized. The formula assumes the model cannot see the structures at all, but the model can now half see them, and the assumption underlying the formula quietly breaks. Improving the resolution has made the model worse in a specific and hard-to-detect way. Operational forecasting centers are being pushed into that regime right now, and there is no clean way through it that does not run straight back into the closure problem. Let me state that as plainly as I can. The uncertainty in one of the most consequential numbers of the 21st century is dominated by a 130-year-old unsolved problem about swirling air. Then there is fusion, where the problem takes its most acute form. A tokamak confines a plasma at over 100 million degrees inside a magnetic bottle. From the beginning of the program, the plasma leaked heat outward far faster than theory predicted. So much faster that the discrepancy got its own name, anomalous transport, which is a wonderfully understated way of saying, we do not know where the heat is going. We do now, broadly. It is turbulence, the steep temperature and density gradients that confinement itself creates are precisely the conditions that drive instabilities, and those instabilities generate turbulent eddies that transport heat across the magnetic field lines and out of the machine. Confinement creates the gradients create the turbulence destroys the confinement. Predicting how a machine like ITER will perform therefore requires predicting that turbulence, which is done with gyrokinetic simulation, among the most computationally demanding calculations performed anywhere in science. The economics of fusion power, an enterprise on which tens of billions of dollars and a good deal of hope have been spent, turns substantially on a turbulence prediction that nobody can make with confidence. And then it is simply everywhere else. Wind farms lose 10 to 20% of their potential output because turbines sit in the turbulent wakes of the turbines in front of them, and predicting those wakes well enough to lay out a farm optimally is a turbulence problem. Ships lose most of their propulsive energy to friction along the hull. Systems that inject clouds of microbubbles into the boundary layer are in commercial use and deliver a few percent. Every pipeline, every pump, every heat exchanger, every ventilation system is oversized to cover the uncertainty. Combustion in a jet engine works only because turbulent mixing brings fuel and air together fast enough. The flame exists because the flow is chaotic, and arterial plaque forms preferentially at bends and branch points in the circulation, exactly where flow separates, and the shear on the vessel wall becomes disturbed and oscillatory, which means the geometry of turbulence has a hand in the leading cause of death in the developed world. None of these are unusual cases. That is what I want to leave you with before we go looking for hope. It is not that turbulence causes trouble in a few specialized industries. It is that essentially every process in the modern world that involves something moving through something else runs into it. And in every one of those cases, the response is the same. Measure, fit, tune, add margin, and hope you are not operating outside the range where the model was calibrated. Civilization has quietly built itself on top of a physics problem that was never solved, by wrapping the whole in enough empirical data to walk across. Add all of it together, and the estimates for what a genuine solution would be worth run into the trillions of dollars. That figure is soft by its nature. It involves assumptions about how much of the theoretical gain could be captured in practice, but the direction is not in dispute. Turbulence is one of the largest efficiency taxes levied on industrial civilization, and it is levied quietly, in fuel burned and heat lost and margins added, on everybody, forever. Nobody sends the invoice. It is simply folded into the price of moving anything, anywhere, and it has been folded in for so long that it looks like the natural cost of doing business rather than the cost of an unanswered question. So that is the bill, which makes the obvious question rather urgent. Is anybody actually getting anywhere? As it happens, in the last 4 years, yes. And the way they are doing it would have been unrecognizable to every person we have met tonight. In the last 4 years, 2 things have happened that make this the most interesting moment in the history of the problem since Kolmogorov. Both of them involve computers doing something computers have not previously done in mathematics. Not calculating faster, proving. The first comes out of Caltech, from Thomas Howe and his former student Jiajie Chen, and it concerns a close relative of the Navier-Stokes equations called the Euler equations. The Euler equations are Navier-Stokes with the viscosity removed. They describe an idealized fluid with no internal friction at all. And it is important to understand that removing viscosity does not make the problem easier, it makes it, in a specific sense, more dangerous. Viscosity is the only term in the equation that dissipates energy, the only mechanism that smooths sharp features out. Take it away, and there is nothing left to stop the vortex-stretching feedback loop from running away. If any fluid equation is going to produce an infinity, Euler is the obvious candidate. The story starts in 2014, when Ho and a collaborator, Guo Luo, ran a very careful numerical simulation of a swirling flow inside a cylinder. What they found was a scenario in which, right at the boundary where the swirling fluid meets the wall, the vorticity appeared to be heading for infinity in a finite time, and, crucially, the solution appeared to be approaching a self-similar shape as it did so. It was reproducing its own form at smaller and smaller scales, faster and faster, exactly the pattern that a blow-up requires. But a numerical simulation is not a proof. Computers work in finite precision. A calculation that appears to run away to infinity might be doing so because of accumulated rounding error, and this has embarrassed people before. For 8 years, the Ho-Luo scenario sat there as the most convincing numerical evidence anyone had, and as something nobody could establish. What Chen and Ho did, announced in 2022, was to turn it into a theorem, and the structure of how they did it is worth understanding because it is a genuinely new kind of mathematics. They began with a human-written analytic framework. The trick is to change coordinates so that the shrinking, accelerating blow-up is transformed into a steady picture. You zoom in and speed up at exactly the rate the singularity is developing, so that in the new frame, the solution stops moving. In those coordinates, the question of whether a singularity forms becomes the question of whether an approximate steady shape is stable. If a solution near it stays near it, the blow-up happens. Establishing that stability requires a great many detailed numerical bounds, and this is where the machine comes in, but not in the usual way. They did not use ordinary floating point arithmetic, which produces a single approximate number with an unknown error. They used interval arithmetic, in which every quantity is represented not by a value, but by a pair, a guaranteed lower bound and a guaranteed upper bound, and every operation propagates those bounds rigorously. When such a calculation tells you a quantity is less than 1, it is not saying probably less than 1. It is a mathematically certain statement, with the rounding accounted for in the arithmetic itself. It is worth pausing on how unusual it is for a proof to contain a computation. Mathematics has been uneasy about this since 1976, when Kenneth Appel and Wolfgang Haken proved the four-color theorem, the statement that any map can be colored with 4 colors so that no 2 adjacent regions share one, by reducing it to roughly 2,000 cases and checking them all by computer. The proof was correct. It was also unreadable, and a significant number of mathematicians at the time refused to regard it as a proof at all, on the grounds that a proof is supposed to explain, not merely certify. That argument has never entirely gone away, and it is about to become much more pressing. The Chen and Ho work is not 2,000 cases. It is an enormous body of rigorous numerical estimation that no human being will ever check line by line. What you are trusting is the interval arithmetic, the implementation of it, and the framework around it. Those are all checkable in principle. Nobody is going to check them the way one checks a page of algebra. The result is a proof, finite time blow-up of the 3-dimensional axisymmetric Euler equations, with smooth initial data and a boundary. Real, rigorous, and partly executed by a machine. Now I have to be careful, because this is the point where reporting on this subject usually overreaches. This does not solve the millennium problem. Euler is not Navier-Stokes, and the missing term is precisely the one that might prevent everything they found. Viscosity becomes more and more effective as structures get smaller, and it is entirely possible that it always wins the race in the end. The boundary matters too. The clay problem is posed without one. What the result does establish is that fluid equations of this family really can tear themselves apart, that the self-similar root is the right thing to be looking for, and that this hybrid method, human framework, machine-certified arithmetic, is powerful enough to settle questions that resisted purely human attack for decades. Which brings us to the second development, and to a room where nobody was looking at a fluid at all. In September of 2025, a team at Google DeepMind, working with mathematicians at Brown, New York University and Stanford, announced that they had systematically discovered new families of singularities across 3 different fluid equations. They did it with physics-informed neural networks, and the way these work is worth a moment. An ordinary neural network is trained on examples. You show it 1,000,000 photographs and correct it when it is wrong. A physics-informed network is trained on an equation. There is no data. The network proposes a function. You check how badly that function violates the differential equation, and you adjust the network to reduce the violation. Over and over. The network is not learning from the world. It is being punished, continuously, for disagreeing with the Navier-Stokes equations until it stops disagreeing. Picture what that run actually looks like. There is a screen with a number on it, the residual, the measure of how badly the current guess violates the physics. At the start, it is large, and the shape on the screen is meaningless. Over hours, the number falls, through a 1/10, a 100th, a 1,000th, down through orders of magnitude, and as it falls, a form begins to resolve. A profile appears, a specific, structured, self-similar shape describing how a fluid concentrates itself toward an infinity. Nobody drew it. No experiment has ever produced it. It was extracted from the equation itself by a machine that was told nothing except satisfy this. There is a second reason the physics-informed approach fits this problem so neatly, and it has to do with what the network is actually good at. A blow-up profile is self-similar, the same shape repeating at ever smaller scales. A conventional numerical grid handles that badly because a fixed grid resolves the large copies and loses the small ones, and refining the grid indefinitely is exactly the cost problem we have already met. A neural network does not use a grid. It represents the solution as a continuous function with adjustable parameters, which means it can hold structure across many scales at once without paying for each scale separately. For most purposes, that is a modest technical advantage. For hunting self-similar singularities across a wide range of scales, it is close to the ideal tool, and the fact that it turned out to be the ideal tool was not the reason it was invented. The reason this particular result matters so much is the word unstable. A stable singularity is one you could find by brute force. Set up a simulation, run it forward, and the flow falls into the singularity on its own. Small errors get pulled back toward it. That is what the Holuo scenario is. An unstable singularity is the opposite. It sits on a knife edge. It is a solution the equations permit, but any deviation at all, any rounding error, any numerical imperfection, pushes the solution off it and away. Running a simulation forward will essentially never find one, in the same way that you will essentially never balance a pencil on its point by dropping pencils. And here is why that matters for the $1 million. There is a widely held conjecture in the field that any singularity in the Navier-Stokes equations, if one exists, must be unstable. The intuition is that a stable one would be so easy to stumble into that we would have seen it by now, in a simulation or in the world. If that conjecture is right, then the object everyone has been hunting for the last 50 years is precisely the kind of object that no ordinary method could ever find. We have been dropping pencils and concluding that pencils cannot balance. The deep mind work found unstable ones, not in Navier-Stokes itself, but in related fluid equations, and, this is the operational point, to a precision the team reported as good enough to feed into a computer-assisted proof of exactly the Chen and Ho type. So the two developments fit together. One team built a method for turning high-precision numerical shapes into rigorous theorems. Another built a method for finding shapes nobody could find before. Neither has solved the problem. But for the first time, there is a plausible route, made of two pieces that were each invented in the last 4 years. There is something strange waiting at the end of that route, and it is worth naming. If this problem is resolved by these methods, the proof will be a hybrid, a human argument whose critical estimates are certified by machine arithmetic that no person could check by hand, running to computations that would take a lifetime to verify manually. It would be a resolution nobody can hold in their head. 180 years after Navier, the answer to whether water behaves may arrive in a form that only a machine can read. And that leaves one thing left to settle, the question I asked you at the very beginning, and have not answered. So let me answer the question I asked you 2 hours ago, plainly, and without holding anything else back. I said that every problem in physics has an answer, or at least a clearly shaped hole where the answer will eventually go, except one. The one is turbulence. And I want to tell you exactly why it earns that description. Because it is not simply that it is difficult. Plenty of things are difficult. It earns it because of the shape of the ignorance. Think about the other great open problems. We cannot describe what happens at the center of a black hole, because we do not have a theory that combines gravity with quantum mechanics. The missing thing is a theory, and everybody knows it is missing, and finding it is the work. We cannot say what dark matter is, because we have not detected the particle. The missing thing is an observation. We cannot explain why the Higgs boson has the mass it does. The missing thing is a mechanism. In every case, there is a hole, and the hole has an outline, and you could recognize the answer if it walked in. Turbulence has no hole. Nothing is missing. The equation is complete and correct, and universally accepted. Every quantity in it can be measured. The initial conditions can be specified to whatever precision you can afford. There is no unknown force, no undiscovered particle, no regime where the physics might change. It is classical, it is non-relativistic, it is not quantum, and it lives entirely inside the portion of physics that everyone agrees was finished before your great-grandparents were born. And it cannot be answered. That is the distinction. Every other unsolved problem in physics is unsolved because we do not know enough. This one is unsolved despite our knowing everything relevant. The obstacle is not in the world, it is in the relationship between a law and its consequences, which is the sentence I planted with you back at the beginning, and which has picked up a great deal of weight since. We can write the law and still not know the outcome. When I first said it, it was a paradox, a strange-sounding claim about water. Then it acquired a mechanism, the non-linear term, the flow acting on itself, energy handed down a chain of scales with no separation between them. Then it acquired a mathematical shape, the closure problem, in which averaging generates unknowns faster than it removes them, and Tau's supercriticality barrier, which does not merely say that nobody has found a proof, but that whole classes of proof are provably incapable of working. And now, at the end, it is something larger than a fact about fluids. It is a statement about the limits of a particular way of understanding the world. The promise of reductionism, the engine of 400 years of extraordinary success, is that if you find the rules governing the parts, you understand the whole. Find the law, and the behavior follows. It has worked so well, so consistently, in so many domains, that we have stopped noticing it is a promise rather than a theorem. Turbulence is where the promise is visibly not kept. The rules of a moving fluid fit on a single line. They are simpler than the rules of almost anything else in the physical sciences, and the behavior they generate has defeated 180 years of continuous effort by some of the finest mathematicians who have ever lived: Stokes, Reynolds, Richardson, Kolmogorov, Leray, Ladezhenskaya, Caffarelli, Tau. Knowing the rules of a system is not the same as knowing the system. That is the lesson, and it is not a comfortable one, because it invites a question with a very wide scope. If it is true of water in a pipe, the simplest continuous thing anybody can name, governed by a law nobody disputes, then what else do we believe we understand merely because we can write down its equation? It is worth asking that question seriously rather than rhetorically, because there are candidates. Protein folding is a system where the underlying physics is known, and the outcome was, until very recently, uncomputable in practice. And the tools that finally made progress there were statistical and learned rather than derived, which should sound familiar after the last part. The behavior of a neural network with 1 trillion parameters is fully specified by arithmetic that anyone can write down, and nobody can predict what it will do without running it. An ecosystem obeys chemistry, a brain obeys physics, a market obeys accounting. In each of those cases, we have the rules of the parts, and no route from the rules to the behavior. Turbulence is the cleanest example, and the oldest, and the one where the gap has been most rigorously demonstrated. But it may not be the exception. It may be the first clear sighting of something general. There is a remark I left with you near the beginning, and it is time to bring it back. In 1932, Horace Lamb, in his 80s, having spent a career on fluids, said he hoped for enlightenment on 2 matters after his death: quantum electrodynamics and the turbulent motion of fluids. And about quantum electrodynamics, he said, he was really rather optimistic. It reads as gentle, donnish wit. Look at what actually happened. Quantum electrodynamics, the thing he was pessimistic enough about to put on a list of afterlife questions, went on to become the most precisely verified theory in the history of science. Within 20 years of his remark, Feynman, Schwinger, and Tomonaga had it working. Its prediction for the magnetic moment of the electron now agrees with experiment to around 12 decimal places. It is not merely solved, it is the standard by which we measure what solved means. And turbulence is exactly where he left it. The equations are the same equations. The closure problem is the same closure problem Reynolds identified before Lamb gave that speech. The Millennium Prize is unclaimed. 94 years on, a man who was pessimistic about the wrong one of his 2 questions turns out to have been being generous. And I want to be careful not to leave you with the impression that this is a story of failure, because it is not. Look at what came out of the attempt. Reynolds gave engineering its most useful number, and it is used in every discipline that touches a fluid. Richardson invented numerical weather prediction, which now saves thousands of lives a year, and stumbled into fractal geometry on the way out. Kolmogorov found a genuine universal law in the middle of the chaos, and it holds from the laboratory to the interstellar medium. Leray invented the weak solution, which is now the foundation of the entire modern theory of partial differential equations, and he invented it because this problem would not yield. Lorentz found chaos itself, an idea that reshaped biology, economics, ecology, and epidemiology, because he was trying to forecast the weather and had a coffee break. Not one of them solved it. Every one of them came back with something enormous. There is a lesson in that too. The value of a hard problem is not confined to its solution, and some of the most useful mathematics of the last century exists because water refused to cooperate. Now, come back to the tap. You are standing at the sink, and the water leaves the spout as a clear glass rod, and somewhere a few centimetres down, the column breaks. You know now what is happening at that boundary. Inertia has beaten viscosity. The Reynolds number has gone past a threshold that is not really a threshold, in a room whose quietness is part of the answer. Below that point, energy is pouring into swirls the width of the stream, and those swirls are breaking into smaller ones, and those into smaller ones, down through the whole cascade Richardson described in verse, distributing itself as Kolmogorov said it would, approximately, for reasons nobody can derive, until the eddies are small enough for viscosity to finally convert the motion into a tiny amount of heat in your sink. And you know that nobody can tell you where that break will be, not because the physics is unknown, because knowing the physics is not enough. That is the thing I most want to leave you with, and it is the reason this problem matters more than the others rather than less. Every other great open question in physics is somewhere you cannot go, the singularity inside a black hole, the first instant of the universe, the interior of a proton, distances and energies and moments that no human being will ever be present for. This one is the air in the room you are lying in. It is the water in the pipes in the wall. It is the weather over your house tonight, which is why the forecast stops meaning anything after 2 weeks. It is the smoke off a candle, the cream in the coffee, the wake behind a boat. It is the breath currently moving in your chest, which becomes turbulent in the larger airways before it settles into smooth flow in the smallest ones. It is the blood leaving your heart, which is disturbed and unsteady in the aorta with every beat. Every other unsolved problem is far away. This one is the medium you are suspended in, going in and out of you several times a minute for your whole life. Every problem in physics has an answer, except the one that matters most. And the reason it matters most is that it is the only one you are standing inside of. Thank you for spending this time with me, following one very old problem all the way down. If this kind of slow walk through something nobody can solve is how you like to end the day, a like or subscribe would mean a great deal. It helps me keep making these. And remember, the next time you turn on a tap and watch the water go from glass to white, that you are looking at the edge of what physics can do. Good night, and may you never look at moving water the same way again.